present. Okay, so if you were in Berlin, maybe you saw some of this talk already. It's similar to the talk I gave there, but now this drawing is in color, so it was well worth it attending this talk already. I imagine many of the attendees here know SNARKonomicon. It's an ancient, text. It was written in 2016. It has no, I don't know. Okay, so let's see. Does anyone know which button I pressed?
You have to point it on your laptop.
Okay. Okay, all right, totally. So, okay, so who am I? Oh. It's the left button to go forward. Or maybe I'm holding it upside. I was holding it upside down. Okay. So, right. Okay, so I'm Izaak. I work on a cryptocurrency protocol called Coda, and also a SNARK programming language, which is similar to what Kathy showed us earlier, called SNARKy. That's the logo. It's very evocative of maybe what's going on. So Coda is a cryptocurrency that uses recursive composition of SNARKs to help attack blockchain scalability and also accessibility verification. What's cool about it is that anyone can use the SNARK, verify the whole chain even on a phone just by checking a SNARK. And there will be a workshop on recursive composition later, so if you're interested in learning more about recursive composition, you can come to that. So I think, maybe I'm wrong, please, I apologize to all the people in the audience. I think I've written probably about as much SNARK code as anyone else. I think, at least with these modern systems. There are obviously some people in the audience who are I think, maybe will tell me they've done more. But so I'm going to try and communicate some of what I learned in that process because, well, there are a lot of tricks of the trade that are maybe only known by a very small number of people. Maybe a lot of them are in this room, actually. So, who has programmed SNARK, I guess? Oh, wow, this is amazing. So, yeah, right. I mean, of course, I see the people who, right. I learned a lot from reading their code. And who knows at least what I mean by SNARK programming? Okay. So, just maybe this is beating a dead horse at this point, but the functionality of SNARKs, what's the deal? So just so we have some language. For a given program P, let's say with 2 arguments and some public value x, what you prove is I know some secret y, right? So that if I evaluate P on x and y, then it'd say the output is 0. Okay, sure, right? And it's a SNARK, so the proof should, the ZK SNARK say, the proof should reveal nothing about this y should be a secret, and it should be small. And it should be easy to check. Regardless of how complicated P was, let's say. So I said program, right? So P is a program. So what is a program? Well, it's a program in some programming language. You can't talk about a program without talking about a programming language, unless maybe you're a cryptographer, in which case you say it's a circuit or something. So maybe it's x86 assembly, maybe it's C, maybe it's Python. I don't know. Maybe it's even Haskell. Who thinks it's any of these? No. Yeah, it's not, right? It's something else. So what else? Well, that's the question, what is SNARK programming? It's writing programs in that something else. And it's mostly programming this function P, but it's not entirely programming this function P. You also have to sort of program, there's sort of other parts of the program that are not just this function P. So, but that's actually a little out of scope for this talk because that's maybe considered that's even more arcane than what I'll talk about. Okay, so it's programming this function P, but it's with a different sort of machine model than most people are used to. Just to set up language, just to be really crystal clear, computer program, it means, to me anyway, a program which is intended to be executed on CPU. SNARK program means to me anyway, program intended to be executed on, quote unquote, on SNARKs. Okay. So, and this isn't really true. I mean, some of what I'll say also applies to I think pretty much everything applies to bulletproofs, and some of it applies to STARKs. Okay? But not all of it, but a lot of it. Okay, so what's different in this world from in the world of normal programming? Well, okay, so first of all, the cost model, what's efficient and what's not, which many people have alluded to in various ways. And second of all, the fact that you have access to non-determinism. Okay? So And also there's this fact that you can only sort of directly access a long amount of data at once, but that's also out of scope. I'm not going to talk about it. So, okay, the cost model. We should look at the primitives that you have access to in each situation. So on a normal computer, you have maybe arithmetic, 64-bit integer arithmetic, let's say, right? You can access memory, you can do bit stuff, you know? And you can do and or, and then maybe you can do conditionals. So you can do a while, and you can do an if or whatever. So what can you do in a SNARK? Well, as everyone knows, you can do plus and times some mod some large prime p. It's important to note that plus, at least in the pairing-based SNARKs, costs sort of 0, and times costs sort of 1. Okay. So, okay, what else can you do? Well, actually, nothing else, pretty much. So, I said, that's it, with an exclamation point, like, I'm excited about it, but you might say, that's it, like, panicked. Well, okay, so, you might say, okay, this seems really bad, and then the SNARK demon is going to haunt you. But, and oh, right, so I also put this joke in, which is, this is maybe how you think about SNARK programming. This was by Bosch in 1575. He anticipated many of these SNARK constructions. But actually, this, first of all, this place looks pretty cool. And second of all, you can also actually do some other stuff. I sort of lied. In particular, this is really where a lot of your power comes from. You can do non-deterministic choice. And you can sort of compute as normal, as long as it's only on values that are statically, okay? Because everyone talks about circuit. Nowhere is there a circuit. There's a Rust program. There's no Camel program. It's a program which generates a circuit. So that's what I mean by you can compute as normal, as long as it's only on values that are statically. Okay. So what's the goal of this talk? It's to show you, at least to suggest to you how to make this a comfortable and exciting place to live. And I want the major takeaways maybe to be that SNARK programming is beautiful and fun, as many people in this room surely know, and that non-determinism is really awesome and fun to program with, but also scary. And it's cool that you can take advantage of field arithmetic. Okay, so I will give examples of the concepts discussed in the Snarky programming language, but it's really such a minimal. The language that I'll use is really sort of. If you ask a programming languages person, told them what an R1CS was, they would write down exactly this programming language. And you ask them, make a programming language that compiles to R1CS, they would write down this language. So it's a really, anyway, I think, sort of the conceptual core of, R1CS SNARK programming anyway. Oh, okay. I don't know what the demon was. Okay, so just, some more words. We'll fix the prime p. For the examples, there's like one example, I'll use p equals 13, but you should think of it as a large number, okay, like 2 to the 56. Please don't use 13 in practice, it won't be secure. No. A number in 0 to p will be the field element. Actually, probably everyone here knows, sorry, I don't want to assume, but like probably a lot of people here anyway know what I mean by field element. Okay, so then let's look at an example. So here's like a really simple SNARK program, I claim. Who knows about elliptic curves? It's a great room. So that's an elliptic curve. As everyone knows, that's a Weierstrass equation for the curve. One thing you might want to do is to compute this polynomial, say, right? This x cubed plus ax plus b. As I said, a SNARK program is a program where you can do plus and times, mod p. Okay, so here's a program that computes that polynomial. It takes x and it returns x times x times x plus a times x plus b. Okay, this is probably the simplest program you could imagine writing. Everyone with me? Okay. So, let me check the time.
It's right there.
Oh, that's great. So, okay, great. So that's a really simple SNARK program, just to familiarize ourselves with the syntax, whatever. Now let's talk about non-determinism because it's cool. So sometimes it's the case that checking something is a lot easier than computing something, which probably everyone here knows too. And non-determinism, as a programming language primitive, lets you, instead of writing the program for computing something, write the program for checking that thing, right? And that's, in the context of a SNARK, just as good as writing the program that computes the thing. So, probably, again, the simplest possible example is division. So okay, so let's say I want to do x divided by y in my field. In other words, I want to compute a z such that z times y equals x. Well, okay, first of all, let's just this sounds trivial, but probably everyone also understands this is an important function of y because you use it for elliptic curve arithmetic, which then you use for everything. Okay, so deterministically, you can only do plus and times. How are you going to compute x divided by y? Deterministically, probably you would, I don't know, maybe you use Fermat's little theorem, okay, which says that if you if you multiply enough, then it's like dividing. Right? Okay? It's a famous theorem from group theory, from finite group theory. So it just tells you if you want to divide by y, you can just exponentiate y to p minus 2, and that's the same thing as like inverting it. Yeah. So, but that's kind of crappy because it's how are you going to do that? Well, you're going to have to do like log p multiplications, right? If you want to exponentiate to p minus 2, maybe less if you got really lucky and your prime's really nice, but roughly. I guess not luck. People choose primes for that reason. But so this is bad. Okay. So on the other hand, right, 256 is a big number, and that's the idea of this slide. Okay. Okay. What about checking? Well, this I claim is a lot easier. If someone gave you z, how many multiplications would you need to check that z equals x divided by y? Who knows? I see some fingers in the air, which I assume people is their answer, which is 1. You just need 1. Why? You just check that z times y equals x, right? Easy. Okay, great. So how can we, Kathy said something before about allocating variables and whatever, and usually people, when you program SNARKs, you understand what this means. You're adding another witness or whatever, but for me, that's not, at least, that's not good for me. I don't, I prefer a way of talking about it that has, in my mind anyway, semantics that are more understandable to me, which is, you can imagine augmenting your programming language to have some kind of guess and check power. Okay, so let's say you have a magic guess function, and I call it exists. Okay, so it's a function that it just returns something. Okay, you guess, and then you have a check function which lets you make assertions, which you can imagine halt execution if those assertions fail. Okay, and I will call that assert. I don't know why I didn't call it guess and check, but okay, yeah, oh well. So for example, just to just explaining the words. Here's like what division would look like. First you guess a z, then you check z times y equals x, then you pass back z. Yeah? Okay. And just to help us understand the semantics, when you say guess, you can imagine execution. This is how you have to think about it. You can imagine execution occurs for every possible z, every possible guess, and then the check occurs in every possible branch. Okay, so you check 3 times 2 equals 6, yay. You check 4 times 2 equals 6, bad. You check 5 times 2 equals 6, also bad. And the branches for which the checks pass, those are the ones along which computation continues. Okay, so this is just how to think of it in non-determinism. So, right, okay, so for div 6-2, if we guess 3, then we pass the assertion and we can say then that div 6-2 equals 3. Okay, in semantics. Div 1-2, we guess 7. We can check 7 times 2 equals 1. I said mod 13. So we can say in semantically div 1-2 equals 7. Div 0-0, I don't know, maybe 0. That's a good guess. We check 0 times 0 equals 0. Okay, that's good. So we can say div 0-0 equals 0. Like div 0-0, we guess, I don't know, maybe it's 5. We check 5 times 0 equals 0. And okay, so we can say div 0-0 equals 5, right? So, okay, well, all right. So we said div 0 equals 0, div 0 equals 5. And now we think maybe the SNARK daemon is coming back to haunt us because it's a scary semantics when functions can have in principle multiple values. So well, what you can do about this is you can maybe add an assertion that says y is not 0, and that would fix this problem. But this would cost one extra constraint, or one extra multiply. Or you could just change the name of the function from div to div unsafe, and that's also something you can do. Or you can use a type system that sort of tracks whether something is 0 or not. And if you're interested in that, then come to the formal verification workshop. Okay, so yes. Okay, so now let's see the syntax in the programming language. So it would just look like this. You say div xy, it's a function. You say z is use the exist function to guess a value, and then assert that z times y equals x, and then return z. So this isn't really the whole program. I allotted some details about how to compute z, but okay. Anyway, makes sense? Syntax? Okay. Seed time. Okay, great. So, okay, revisiting our example. Yeah, well, I want to get to the more interesting stuff. I'm just going to keep going. We're just going to skip this. Okay. So, yeah, this is important. This one maybe not so fun. Okay, so takeaways for non-determinism. Right. So when you try to write, when you're writing non-deterministic programs, it's good to think in terms of specs instead of algorithms. It's extremely important to use non-determinism. You can't get away from using it if you want to make your SNARK programs efficient. But as we saw, it's very scary. It's very scary. Your program, if you do div 0, 0, your whole system, you could be hosed. So the best thing to try and do is to try and build abstractions that use non-determinism internally, but hopefully don't leak it if you can manage. Okay, so let's see. Let me just say a few words about taking advantage of arithmetic. So there are non-tricky techniques. These are techniques which make sense, like using elliptic curve-based primitives. For example, everyone knows like the Pedersen hash function, especially the one that Sean and Darren made, is 20 to 30 times more SNARK efficient than SHA or Blake 2. You can simulate an integer arithmetic, right? You have a finite field, so you can also simulate integer arithmetic. That's also useful and non-tricky in the sense that it makes sense. And then there's tricky techniques, like, I don't even know, like packing. Okay, I won't talk that much about it. And then there's this, like, using the fact that sum is free to do sort of search over a big array. That's also a useful technique and kind of tricky, in that it involves a trick. Well, it's kind of a trick. But let me just explain this, and we can get a sense for the people who haven't done SNARK programming. We can have one more example in your SNARK toolkit, and then I will talk about something else. So, bools, right? So bools you represent using field elements which you know are either 0 or 1. Okay, this is a friendly representation of booleans for if you're a computer scientist, or let me say like a non-programming language computer scientist. And then, negation, writing these things in terms of arithmetic is really easy. Like negation is just 1 minus, and is just multiply, or you can just do De Morgan. And then, okay, so let's say, for example, you want to OR a whole bunch of bits together, right? So one way of doing it would be to sort of take your n bits and OR them, just put ORs in between all the bits, you know what I mean? So do it, okay, right, do n OR, do n minus 1 ORs. And this is actually kind of crappy, well, maybe depending on your point of view, because this costs n minus 1 multiplies, right? For each OR, we have to do 1 multiply because of that and there, and so that's kind of crappy. But taking advantage of the fact that addition is free, this is a trick that I guess I learned from reading libsnark code, which is you just take your bits and you add them up, right? They're 0, 1, so you just add them up, and then you just say, oh, just check that like if I add up all the bits, it's not 0. And checking if something is not 0, like, I won't write it, but believe me, it costs 2. So this whole thing costs 2, regardless of how many, 2-ish, regardless of how many bits you're ORing together. And there's a whole bunch of similar things that sort of fall into this same bucket of just like adding a bunch of things up, or maybe taking a linear combination of things instead of doing things one by one. Okay, so all right, there's that equal. Okay, so yeah, it's good to exploit addition being free. Aha. Okay, this is something I didn't talk about in my other talk. So if this is the new thing. So this is an advanced and really horrible technique that this is like the most scary kind of technique. So it's doing optimizations which are locally, they sort of look unsound, okay? But globally, actually, they're sound. And I put this image because I guess I was trying to think, okay, what's a metaphor? It's kind of like jaywalking. You know? Like jaywalking, you see the don't walk sign, you're like, yeah, I'm not supposed to walk, it's wrong if I walk. But, you know, sometimes there's no cars coming, so it's okay, right? And actually it's better, because you save time. As long as there's no cars coming. So, but if there are cars coming, right? So, actually sometimes it's even worse. You do something which is sort of is globally sound, but only sort of computationally. But that's fine, because it's cryptography. So, right, it's kind of like jaywalking. What's an example? Actually, a very good example is and I had a conversation with some people before about this, so I apologize, this is what I said to you before. It's unsafe curve addition. So, it's actually only kind of an example, sorry, I forgot. I realized because you can actually sort of formulate a local property with respect to which it's safe, but which will be important for formal verification, but this was kind of the simplest example to talk about, so I just wanted to go with it. So, okay, so remember we had this div function, which I've renamed to div unsafe, because I'm a very responsible programmer. Inheriting from this, from this div unsafe function, you can define add unsafe for two elliptic curve points, okay, like A and B, now find coordinates, and it invokes div unsafe, so you know maybe something scary is going on, and you look at that and you see, okay, something bad happens if by is equal to ay, and bx is equal to ax, so if a is equal to b. So if the 2 points are identical to each other, then something bad happens. So it's unsafe if a equals b, yes, exclamation point. But why would you do this? Like, why don't you just use the safe version, right? Well, okay, as I said, like, add unsafe, it's 3 constraints, and we can make it safe with 1 more constraint, just like with division, but, you know, that's 33% worse. So we should really avoid it if possible, especially because the main thing that the main cost in a SNARK is doing Merkle trees. And doing Merkle trees is just doing a bunch of Pedersen hashes, and each of those is, elliptic curve operations, so you do it a lot. So 33% worse is bad. What can you do here? Well, okay, so the Pedersen hash, right, I was just saying, you take some scalars, okay, x0 up to xn, maybe they're bits, imagine they're bits, the simple version, and you compute this sum, x0 to 0 plus xn gn, where the gi's are random elements of the group. And you compute it in the following way. You compute it inductively, so you can compute a prefix, right, and then you add on 1 more, and then you add on 1 more, and you add on 1 more, and so on. And what you want to know is that each of these add-on 1 mores, you'd like to use add unsafe to add on that 1 more, so you can save your 1 constraint. And so what you need to, what you need to know, what you can prove actually is that if the GI are chosen uniformly at random, then if you can get an attacker to hit the bad case for add unsafe, then actually that attacker can compute discrete logs. Okay? So you know that actually it's safe to use add unsafe, because if they could take advantage of the fact that you have that in your circuit, then they could compute discrete logs anyway. So that's the kind of optimizations that I was referring to. So this is something which is locally scary, but globally you think about it and actually it's fine. So, okay, so maybe let me add, I wrote this just 2 minutes ago, just some reflections on like why I think it's important to define languages, because everyone's in the same room. When you're using ZKPs, you write them in some programming language, Rust or OCaml, whatever. I think it's good to write in a language with clear semantics, because it's easier to reason about. The word gadget, I guess everyone says it all the time now, so we're stuck with it. But everyone should start to imagine that gadget actually means function, non-deterministic function. Okay. And why is it important to have a clear semantics? It's important for reasoning about things formally and informally. It also makes it possible, maybe, to optimize SNARK programs. Oh, just one plug. So we are doing an open source prover SNARK speed up contest. Hopefully, we'll dramatically improve the state of the art prover, and everything will be free and open source, so everyone can use it. Everyone can have fast SNARKs. It's great. And we're just starting to bring in co-organized speakers, sponsors, participants. So if you're you have some knowledge to share, or money or publicity and want to get involved in whatever, let me know. And in fact, right, there's this URL, codeprotocol.com/snarks. And OK, I think I'm out of time, so I guess I'll just leave it. I'll leave it at that.
OK, terrific. All right, thanks. So I guess we should take still one question. So are there any questions? Yeah, Henry.
So I have a question about the exists check thing.
Yeah.
So in your division example, there's this scary so in the division example, there's this kind of scary non-determinism where maybe this function could have multiple outputs, and then you can make a safe version of it where there's an extra check, and then that check that you add repairs that function so that it only has one output. But that check is specific to the definition of division. So in this programming model, my question is it the responsibility of the programmer when they use this functionality to somehow convince themselves that the function actually does only have one output, whether that's locally to the function or deferred up to this global thing? I
guess it's sort of flexible, so it's sort of up to you. You can make the types as expressive as you want. So you could say, this division function takes a pair of points. You could write this type, right? I mean, you can imagine a programming language where you could write this type. It's not literally this way, but you can imagine it. This takes a pair of points, not both of which are 0.
But it is in at some level the responsibility of the programmer when they use this functionality to ensure that there is only one output.
Well, yeah, or they don't care maybe. But you can sort of automate that with the type system as much as you care to.
Well, I think the example you skipped, you did the curve addition where they're actually, or you found the point in the curve.
Yeah,
where there
right.
really are two outputs,
right.
Which
sometimes you care, sometimes you don't care.
Right.
Yeah.
And by the way, your add function did not check that the points were on the curve.
Right. The assumption is that the inputs were already on the curve. You would also want to type for that.
That's a cardinal sin.
Yeah. Yeah.
Terrific. Okay, so let's move on. Thank you very much, Izaak.